When you think about the most important functions of a router or switch, keeping accurate time is probably not the first thing that comes to mind. But timekeeping that is accurate and consistent across all devices is critical for security protocols, event logging, and troubleshooting. Let me show you why. Imagine this scenario. An OSPF neighbor relationship on router R1 moves to the full state at 1634. Then, 1 minute later, the same neighbor goes down due to an expired dead timer. You check the logs on R1, and everything looks fine. But then you check the logs on R2, the neighbor router, and something is wrong. R1 thinks it is 1710 on August 28, 2023. R2 thinks it is 9:49 on August 8, 2023. The clocks are completely out of sync. Correlating logs between devices becomes nearly impossible. If you have more than 2 devices, all with different times, you will definitely be wishing you had configured NTP. So before we dive into NTP, let us look at how you can manually set the time on Cisco devices. Every Cisco router and switch has an internal software clock. You can view it with the show clock command. Add the detail keyword, and you also get information about how the device learned the time. Some devices also have a battery-powered hardware clock called the calendar. You can view its time with show calendar. When the device boots, the software clock learns the time from the hardware calendar. To set the software clock, you use clock set from privileged exec mode. For example, clock set 1634, August 28, 2023. To set the hardware calendar, you use calendar set. Or you can sync them with clock update-calendar to sync the calendar to the clock, or clock read-calendar to sync the clock to the calendar. You can also change the time zone with clock time zone in global config mode, and configure daylight saving time with clock summer-time, name recurring start, -date-time, end-date-time in global config mode. The default time zone is Coordinated Universal Time, or UTC. But here is the problem. Even if you set the time on every device, their clocks will drift over time. And manual configuration simply does not cut it for a scalable solution. This is where NTP comes in. Network Time Protocol allows devices to automatically sync their clocks over a network. NTP servers on UDP port 123. Memorize that port for the exam. NTP can achieve accuracy within 1 millisecond if the server is on the same LAN, or about 10 to 100 milliseconds over a WAN or the internet. TP uses a hierarchical model called stratum. At the top are reference clocks, like atomic clocks or GPS clocks. These are stratum 0. The servers that learn time directly from a reference clock are stratum 1. These are called primary servers. Servers that learn from stratum 1 are stratum 2, and so on. These are called secondary servers. The upper stratum limit is 15. Stratum 16 means the time source is not reliable and devices will not sync to it. A device can be both an NTP client and an NTP server at the same time. You can also configure multiple NTP servers for redundancy and better accuracy. 2 NTP servers can form a peer relationship, exchanging time information bidirectionally. This is called symmetric active mode. Now let us configure NTP. The most common mode is client mode. You use NTP server with the IP address of the NTP server. For example, you can configure a router as a client of Google and Microsoft NTP servers. Add the optional prefer keyword to favor a particular server. After configuring, use Show NTP associations to see your time sources. The asterisk next to a server means it is the one you are currently synced to. The plus sign means it is a reliable candidate, but not currently used. The address column shows the server IP. The ref clock column shows the server's time source. IST column shows the stratum. You can also use Show NTP status to see your device's stratum in the NTP hierarchy. A tip to speed up NTP synchronization is to manually set the correct time before configuring NTP. By default, NTP syncs only the software clock, not the hardware calendar. Use NTP update-calendar to make NTP periodically update the calendar as well. A Cisco router that is an NTP client does not need additional configuration to become an NTP server. Other devices can use it as their NTP server. This is called client-server mode. A recommended practice is to configure a loopback interface and use that as the NTP server address. Loopback interfaces provide a stable, reliable address that is not dependent on any physical port. Configure the loopback IP as the NTP server on client devices, and use the command NTP source loopback 0 on the server to make it source NTP messages from the loopback interface. If a physical port goes down, clients will still sync through the loopback. You can also use the NTP master command to make the router a primary NTP server using its own internal clock as the reference clock. This is called server mode. The NTP master command is not meant to replace the NTP server command. NTP server links to external servers for accuracy. NTP master provides a backup time source if external servers become unavailable. By default, NTP master makes the device a Stratum 8 server. You can optionally specify a stratum value. There is a third NTP mode called symmetric active mode, which is NTP peering. To configure NTP peers, use the command NTP peer followed by the other device's IP address on each device. Unlike client-server, where the client syncs solely based on the server's time, peering allows bidirectional exchange. Each peer uses the other's time data as an additional reference point, improving overall accuracy. Peering also provides an extra layer of redundancy. If one peer loses connectivity with its servers, it can still sync to its peer. To summarize the three modes, use NTP server for client-server mode, NTP master for server mode, and NTP peer for symmetric active mode. Public NTP servers like Google and Microsoft are open. Any client can sync to them without security checks. But in more secure environments with private NTP servers, we need authentication. A malicious server could provide incorrect time data, disrupting time-sensitive applications. To protect NTP clients, configure authentication. First, on both client and server, create an authentication key using the command NTP authentication -key-number MD5 key. The key number is a numerical identifier, and the key is the actual password. Then, on both devices, specify the key as trusted with the command NTP trusted-key-number. Without this step, the key cannot be used. On the client, add the key and key number to the NTP server command. The complete syntax is NTP server IP-address key-number. Both the key number and the key itself must match between client and server. If either does not match, the client will refuse to sync. You can use the same approach for NTP peers by replacing NTP server with NTP peer. A note: the NTP authenticate command is not necessary when you configure the key in the NTP server command. You will often see it in examples, but it is not required for the scenarios we covered. Let us wrap up. Accurate date and time is critical for network devices, especially for log correlation and security protocols. Manual time setting with clock set works temporarily but leads to drift. NTP solves this with automatic synchronization over UDP port 123. NTP uses a stratum hierarchy from 0 to 15, with reference clocks at stratum 0 and primary servers at stratum 1. Devices can be both NTP clients and servers simultaneously. Configure NTP client mode with NTP server. Use prefer to favor a source, and verify with show NTP associations and show NTP status. Use a loopback interface for stable NTP server addressing. NTP master provides a backup time source in server mode. NTP peer enables symmetric active mode for bidirectional time exchange. And for security, configure NTP authentication with matching authentication keys on both client and server. That covers CCNA exam topic 4.2. Configure and verify NTP operating in client and server mode.